Hello, everyone. Welcome to the AGT seminar. Today, Alexander Gavrilyuk from University of Memphis will tell us about non-existence of some Moore Cayley digraphs. Alexander, please.
Okay, so thanks for inviting me. So I'm going to speak about joint work with Metsugu Hirasaka and Vladislav Kabanov. And as you said, this is about non-existence of some Moore Cayley digraphs. So first of all, I should say that this is not a very new result. It was published in 2021, but as you can see, we finished and submitted this paper in April 2020, so during the lockdown. And we didn't have that many chances to present this result at conferences. So I would like to use this opportunity to fix this. Okay, so the problem of existence or non-existence of Moore digraphs is a counterpart of a famous problem, directed counterpart of a famous problem in algebraic graph theory, the existence of Moore graphs, in particular the Moore graph of valency 57. So I believe that everybody probably knows the definition of a Moore graph, but nevertheless, let me, just in case, recall it. So one way to define Moore graphs is to consider the degree diameter problem. We consider an undirected graph, which is regular of valency or degree k, and has a diameter d, and we would like to maximize its number of vertices. So if you think about a graph which should be extremal in this case, so which should attain the maximum number of vertices, then you can realize that such a graph should have a tree-like structure. So if we pick any vertex and consider the distance partition of this graph with respect to this vertex, then with respect to this vertex, it should look like a tree. So all the edges of this graph must be between the corresponding parts of this distance partition, maybe except for the last part. Because if we have any edges inside these layers, then they will not produce any new vertices. So now if we try to estimate the upper bound to count the number of vertices in such a graph, we obtain this formula. So at every step, the number of vertices increases by a factor of k minus 1. And then we sum them up, so we get this upper bound for the number of vertices in a graph which is regular of degree k and has diameter d. So now if we have equality in this upper bound, then we have what we call a Moore graph. And in fact, such graphs were classified by Damerell and Bannai and Ito independently in 1973. So we have a complete graph, which is kind of trivial example. Then we have an odd cycle. And then we have the famous Peterson graph, Hoffman-Singleton graph. And as I mentioned, the existence of this last possibility, or a Moore graph of valency 57, is one of the maybe main open problems in algebraic graph theory. So in particular, it was shown by Aschbacher that such a graph, putative graph, Moore graph of valency 57, cannot be rank 3 graph, and it was shown by Higman that it cannot be vertex transitive. And I will come back to these Higman's results a bit later today. Okay, so now in this work, we considered a directed version of this problem. So we considered Moore digraphs. So first of all, let me clarify what a digraph is. So digraphs may have arcs as well as undirected edges, which we call digons. sometimes. And in this case, an undirected edge can be considered as a pair of two arcs in opposite directions, like in this picture. Now we say that a digraph is regular with degrees r and z if every vertex is incident to the same number of say r of undirected edges, and it has the same in and out degree z. And this z counts only arcs which are not contained in digons. So in this picture, say this vertex is incident to r undirected edges, and it has z as an in and out degree. Okay, so and now the problem is the same. I mean, we have we can fix degrees r and z and diameter, and we ask what is the maximum number of vertices which such a graph may have with under these constraints. So a similar formula for the upper bound of the number of vertices for digraphs can be derived, but its general form is quite complicated. And in fact, it was shown in 2007 that there are no proper Moore digraphs of diameter greater than 2. So from now on, we can just focus on the case of Moore digraphs which have diameter 2. And such graphs were, so a Moore digraph of diameter 2 can be also defined by the what I'm going to call unique trail property. So for every pair, say ordered pair x and y of vertices of Moore digraph delta, there is a unique trail from x to y of length at most 2. So, for example, if we have a pair of vertices which are connected by an arc from x to y, then we have a unique, now we have a unique trail of length 1 from x to y. So in particular, it means, for example, that in this graph, there are no backup trails like this. Oh, sorry. So in a Moore digraph, there are no backup trails from y to x in this case. So, yeah. Then if we have, for example, a pair of non-adjacent vertices x and y, then they may be connected by a unique trail of length 2, like this. Or if there is an arc from y to x, then they will be connected by a unique trail of length 2, again, like in this picture. Okay, so now Moore digraphs of diameter 2 were considered much earlier in 1979 by Bosák. So he proved the following results. Let delta be a Moore digraph of diameter 2 with degrees r and z. Then we can compute the number of vertices of delta as follows. So this is the number of vertices. And one of the following cases occurs. So we have z equal to 1 and r equal to 0. And such a digraph is just a directed recycle. Yeah. Then we have an undirected 5-cycle. And the last possibility, which is most interesting, there exists an odd positive integer c such that c divides this product, and r equal to 1/4 of c squared plus 3. So in particular, if we substitute z equal to 0 in the last case, then we will have r equal to 3, 7, and 57. So this theorem also covers the undirected case. So we can recover the Peterson graph, Hoffman-Singleton graph, and valency 57 graph from the last statement of this theorem. But unlike the undirected case, in principle, we have infinitely many possibilities for the degrees r and z. So we have infinitely many admissible values of r, and for every given r, we have infinitely many admissible values of z. So potentially, we may have infinitely many more digraphs of diameter 2. However, there are only very few more digraphs known so far. So for r equal to 1, the only more digraphs are so-called the Kautz digraphs, which are the line graphs of complete digraphs. So this is a kind of trivial case. And then for r greater than 1, we have only 3 examples known. So the first one is the Bosák graph on 18 vertices with valencies or degrees 3 and 1. This graph is shown on the right of this slide. And 2 Jørgensen graphs on 108 vertices with degrees 3 and 7. And these 3 examples with r greater than 1 are Cayley digraphs. So in particular, this Bosák graph is a Cayley graph over this group or over this group. So it may make sense to look for more Cayley digraphs because of this observation. So this is the motivation for our work to search for more examples of more Cayley digraphs. Okay, so let me briefly recall the definition of a Cayley digraph. So it's same as a Cayley graph, but the difference is that the connecting set in this case doesn't have to be closed with respect to inversion. So in general, we can take any set given a group G, we take any set S, a connecting set which doesn't contain the identity element, and then we split into 2 parts, S1 and S2. So S1 is closed under inversion, and S2 doesn't intersect S2 inverse. And then we define Cayley digraph as follows. So the vertex set is just the set of elements of the group G, and for every element G and every element S from the connecting set S, we draw an arc from G to G times S, and you can see that such a graph has the undirected. So it is RZ regular, where R equals the cardinality of S1 and Z equals the cardinality of S2. And since more digraphs of diameter 2 can be defined by the unique trail property, we can reformulate now this property in terms of connecting sets. So if we additionally assume that Cayley digraph is a Moore digraph, then we have these constraints for the connecting set. So for every element G of the connecting set, there are no pairs S1, S2 such that G equals the product of these 2 elements. And vice versa for every element G which does not belong to the connecting set, there is a unique pair of elements from the connecting set such that G equals the product of these 2 elements. So this is just the interpretation of the unique trail property in terms of the definition of a Cayley digraph. And essentially, this was used by in the result, which I'm going to talk next. So in 2017, Erskine conducted a computer search for Moore Cayley digraphs by using the observation from the previous slide. So it was not a brute force, but very close to kind of brute force search. So he just took all groups of required size and then looked for connecting set and then checked if the corresponding digraphs were Moore digraphs or not. So we have the following now table of small feasible parameters of Moore digraphs and what we know about if they can be Cayley digraphs or if they exist or transitive. So for example, okay, so in the first column, so the first column it is the number of vertices, then the second and third columns are the degrees of corresponding putative Moore digraphs. And so, for example, in the first row, we have the Bosák graph. Which is unique. And as I said, it's a Cayley digraph. Then the next three feasible parameter sets were ruled out by using also a computer search by Lopez, Miret, and Fernandez. So they just show the non-existence of these graphs. So here we have Jørgensen graphs. And for all possible orders up to 486, Erskine showed that these graphs cannot be Cayley digraphs, as you can see in the last column of this table. Yeah. Now, for the last case, for the digraph, a digraph on 486 vertices, it was shown by Jørgensen that such a graph such a Moore digraph cannot be even transitive, vertex transitive. I'm not sure if he published this result, but he presented it in Pilsen at some conference. So the idea is that he showed that if such a Moore digraph exists, this would imply the existence of a certain strongly regular graph. And moreover, if such a Moore digraph is vertex transitive, then the corresponding strongly regular graph would also be vertex transitive. This strongly regular graph is not known, so it's an open case, but it was shown earlier that this graph cannot be vertex transitive. So this implies that, in particular, the corresponding Moore digraph also cannot be vertex transitive. Okay. So now let me speak about our results. So in this work, we reproduced partially the results of Erskine. So we showed the non-existence of some Moore Cayley digraphs, but we didn't use computer search. So we use a kind of algebraic argument to rule out some of these possibilities for the existence of Moore Cayley digraphs. So let me first introduce or just define the adjacency matrix of Moore digraph delta. So it is the 0-1 matrix whose rows and columns are indexed by the vertex set. And in the XY entry, we write 1 if there is an arc from X to Y and 0 otherwise. So it's very similar to the definition of the adjacency matrix of undirected graphs. But of course, it's not symmetric in general. Now, since we have this unique trail property, we can compute the square of the adjacency matrix. So using the unique trail property, we can show that A squared equals this formula. And also, since the graph is RZ regular, we also know that J times the adjacency matrix equals A times J equals K times J. So here J is the all ones matrix, and I is the identity matrix, of course. And in particular, we can observe from this that the adjacency matrix is diagonalizable with 3 eigenspaces. One of them has eigenvalue k, which is the sum of r and z, and there are 2 other eigenvalues, say lambda 1, lambda 2, which are integer numbers, and they can be computed explicitly from r and z. This follows from a more general theory of so-called directed strongly regular graphs. I will not go into details about directed strongly regular graphs, but just this is what we need in our particular case. So now we can define so now we can fix one of these 2 eigenvalues, lambda 1 or lambda 2, and consider the projection matrix onto, say, the right lambda eigenspace. This projection matrix is a linear combination of the adjacency matrix, the identity matrix, and the all ones matrix J. Okay, now let us consider a group of automorphisms, say G of delta, and let us consider a natural linear representation of this group in the vector space over the reals indexed by the vertex set. So we represent every automorphism as a permutation matrix P sub G. And by definition, this matrix commutes with the adjacency matrix. And since the projection matrix belongs to the span of these 3 matrices, we also have that this permutation matrix commutes with the projection matrix E lambda. So now, using this commutativity, we can show that the trace of this product, E lambda times the permutation matrix corresponding to an automorphism G, must be an algebraic integer. On the other hand, again, since the projection matrix E lambda is a linear combination of A, I, and J, we can write this trace as a linear combination of these matrices. So now what we have, so on the right-hand side of this formula, we have a rational expression. The left-hand side must be an algebraic integer. Therefore, the whole value must be an integer. What happens now is that the coefficients of this linear combination, say alpha I, beta I, and gamma I, they are often rational numbers. But they are always rational numbers, but often they are not integer. So this gives us some constraints on the values of the corresponding traces in the right-hand side of this formula. Well, for example, this trace is trivial to compute, is just the number of vertices. So we multiply the all ones matrix by a permutation matrix, and then compute its trace. So it's just the number of vertices. Then this trace, identity times permutation matrix, well, it's just the trace of permutation matrix, and this is the number of points which are fixed by the automorphism G. And now this term, the trace of A times the permutation matrix, has the following interpretation. So this is the number of vertices V of delta such that there is an arc from V to the image of V under this automorphism G. So this term counts the number of arcs like this. in a graph. Okay, so now this is what I called, what we called the Higman-Benson observation, because it was first used by Higman, I think, in his proof that degree 57 Moore graph, putative Moore graph, cannot be vertex transitive. And also it was used by Benson. So he studied automorphisms of finite generalized quadrangles by using this observation. So once again, the observation is that the right-hand side of this formula must be an integer, and this gives some constraints on the number of fixed points and on the number of arcs or edges, like this in the graph. And this allows us to rule out some automorphisms. And more recently, it was used. Similar observation was used by De Winter, Kamishke, and Wang. They studied partial different sets over abelian groups. Okay, so now let me explain how we used this observation in our work. So from now on, we assume that delta is a Moore Cayley digraph over a group G with degrees R and Z. And let's recall that by the Bosák theorem, there exists a not positive integer C, which divides this product. And R equals 1 over 4 C squared plus 3. Now, since we assume that delta is a Cayley digraph over the group G, G is a regular subgroup of the full automorphism group of delta. So we can consider only automorphisms which belong to this regular subgroup. So in particular, for non-identity elements, we can now compute this trace. So the number of fixed points of every automorphism from this regular subgroup equals 0. And this simplifies the Higman-Benson formula. So now this formula simplifies to this one. So we have the following condition, that this quantity must be an integer. So here by A of G, I denoted the trace of this product, A times the permutation matrix. So again, let's know that this quantity, A of G, counts the number of arcs in the G orbits, which look like directed cycles in a graph. And the idea of our proof is that for some orders of a group G and automorphisms from this group, this condition implies that this quantity A of G is too large, so that it violates or contradicts the unique trail property. So we have kind of too many arcs, and it violates the property that for every pair X and Y of vertices of delta, there is a unique trail from X to Y of length at most 2. So we will need a few observations to make it work. So again, as before, let delta be a Moore Cayley digraph over a group G of order, say, n, and let G be an automorphism of a prime order P. So the first trivial observation is that P must divide the number A of G. It is because, as I already observed, A of G counts the number of arcs in the orbits which are directed P cycles. Second, simple but maybe less trivial observation is that if we have an element H of a prime order say Q not equal to P, which commutes with G, then also Q must divide this number A of G. And one more observation is that, so if we have two arcs of this type, so there is an arc from X to the image of X under G to the power of I, and there is an arc from X to the image of X under the action of G to the power of J, then we can find a pair of vertices which violates the unique trail property. Well, here we need to assume that I plus J is not equal to 0 modulo P. So it is because, okay, for example, if we have this arc, and then we can apply the automorphism G to the power of J to this arc. So this would shift this arc and, oh, sorry. Yeah, this would map this arc to this one. And similarly, if we apply the same argument to this arc, we get this arc. So we get quadrangle. So we get two trails of length 2 between this vertex and this vertex. And now we can use this simple observation in order to count arcs. So we can show that using this observation, we can show that this sum does not exceed 2 times the number of vertices. And also, I would like to note that in this formula, so G is an element of order P, prime order P. So in this formula, all the powers of G are also P elements. So G to the I. Okay. Okay, so now let's see how these observations help us to rule out some feasible parameters for Moore Cayley digraphs. So let's consider this example, a putative Moore digraph on 88 vertices with valencies degrees, sorry, 3 and 6. Okay, so let's assume that this Moore digraph is a Cayley digraph over a group of order 88, and G is an element of prime order P. So by Cauchy lemma, we may assume that P equals 11, and then the Higman-Benson observation implies that this expression must be an integer. So therefore, A of G is greater than or equal to 11. Now, by using the Silov theorems, we can show that there exists an element of order 2 which commutes with G, and by the above observation, A of G must be also divisible by 2. So A of G must be greater than or equal to 22. But if you substitute 22 into this formula, you get a non-integer number. So again, by repeating the Higman-Benson observation, we obtain that A of G must be greater than 44. And now we can, so now G is an element of order 11. So we can repeat this argument. So this argument, this inequality now holds for every element of order 11. So in particular, in this formula, we can assume that that every term in the left-hand side is greater than or equal than 44. And this contradicts the right-hand side of this inequality. So the left-hand side would be greater than the right-hand side. So this violates the last inequality, which we proved. So in particular, this shows that there are no Moore Cayley digraphs on 88 vertices. And basically, yeah, okay, so now let me, sorry, let me show you our results. Yeah, so in this table, you can see the non-existence of Moore Cayley digraphs, which was ruled out by Erskine, and which in the last column, you can see the cases which were ruled out by the Higman-Benson observation. So you see that we weren't able to fully reproduce Erskine results, because sometimes the Higman-Benson observation simply does not imply any restrictions, because, for example, this number is always integer. So, but nevertheless, our proof is computer free, and moreover, we were able to go beyond this 486 bound. So we checked all feasible parameter sets up to 2000 vertices, and this observation rules out half of them, of all feasible parameter sets of Moore digraphs on up to 2000 vertices. Yeah, so this observation works well when the number of vertices is divisible by large prime numbers, usually. So we cannot formulate it in general. I mean, for every given order of a Moore digraph, we have to kind of repeat this observation because we have to show the existence of certain elements, and we have to show that there are commuting elements in the corresponding group. So we need to use Silov theorem, for example, and things like this. But yeah, nevertheless, like I said, this is a computer-free proof. Yeah, so that's pretty much all I wanted to say. I just wanted to also say that what we did in this work is kind of cherry picking, because we assumed that, for example, digraph is a Cayley digraph, and so, like I said, this simplifies the Higman-Benson formula, because the number of fixed points equals 0. But in principle, I believe that one can try to use the same idea and to rule out the existence of vertex transitive Moore digraphs. So even for example, for this order 88, we only ruled out the existence of Cayley digraph, but it is still possible that such a digraph may be vertex transitive, for example. But of course, the analysis would be much more complicated in this case. Yeah. Okay, so thank you for your attention.
Thank you for the nice talk, Alexander.
Yeah, thanks.
Any questions for Alexander? So for some of the parameters that your argument doesn't rule out, are there some interesting parameters for R that something that might be interesting?
So what I observed, it's what should I say? It's not like a so what's interesting is that the order of the Bosák graph and the order of two Jørgensen graphs. So it's 18 and 108. These numbers are divisible by 2 and 3 only. And there is another order. I don't remember exactly the number, so it's about 800 vertices, 800 something. So it's another feasible order of a Moore digraph, which is divisible by 2 and 3. And in this case, since this number is not divisible by large prime numbers, our method doesn't work. So it's a maybe there is something about 2 and 3. I don't know. Maybe the next open case when this Moore digraph exists is this. I don't remember the exact number of vertices, so it's about 800 vertices. But again, this number is only divisible by also 2 and 3. But this is kind of, you know, it's not a.
Not enough examples.
Yeah.
Yeah.
So, like I said, the first open case even like 88 vertices, I think. So let me go back to our table. Yeah, so the first open case is 88 vertices. So in this case, we don't know the existence of a vertex transitive Moore digraph. This would be the first maybe example to look at. I don't know.
Yeah, the analysis is, I guess it's to win the graph is abelian or not.
Oh, sorry, say it again.
If you only consider abelian group or some special group, will there be some more tricks to apply? Yeah, I think your analysis doesn't depend on the group structure.
Well, no, for this order, I mean, we know, but yeah. No, I haven't really looked into this case, but
yeah. Thank you. Any other questions for Alexander?
Just have a quick comment. If the group was abelian, then you'd have a strongly regular graph with an abelian group. That's very restrictive assumption.
sorry, can
if you had a strongly if the orthogonal group, if the group you're working with is abelian, and then you get a strongly regular graph with an abelian group acting on it, and they're very strong assumption that implies strong restrictions on the choice of the group. It would be hard to do something which is one pair order.
Oh, you mean something like what the Winter, Kamishke, and Wang used for partial different sets? So it's similar.
Well, it's in Brauer and Neumeyer. They've got some results, but what it was group in their book on disregulated graphs, they have information about the Orthogonal groups, which I can't quite quote correctly at the moment. But the point is that it's having a strongly regular graph with assuming that your Orthogonal group there's an abelian group acting on a strongly regular graph is a very strong assumption.
Yeah, could be.
So, so that you probably can rule out the strongly regular graphs in many cases.
Thank you, Chris. Any other questions or comments? If not, let's thank Alexander again.
Okay, thank you. Thanks again for